Energy is the ability to do work. The unit for energy in the SI system is joules. You might remember that that is the same unit that we had for work. And that's because work and energy are like two sides of the same coin. When we do work on something, we put energy into it. So the unit for energy is joules. And you might remember that a joule is the same thing as a Newton meter. Kinetic energy is energy of motion. When anything is moving, it has kinetic energy. The equation that we're going to use for kinetic energy is 1/2 mv squared. M is the mass of the object in kilograms. It must be in kilograms. And v is the speed of the object. It must be in meters per second. One point of note, when you're using this equation, the only thing that is squared is the v. Don't go 1/2 times m times v and then square that whole thing. Just the v is squared multiplied by m multiplied by 1/2. The unit for kinetic energy is joules. Potential energy is stored energy. And we're going to talk about two types of potential energy. One is gravitational potential energy, which I'm going to symbolize PEG. Gravitational potential energy is what an object has due to its location in a gravitational field. The equation for gravitational potential energy is m times g times h. M you're already familiar with. It's the mass of the object in kilograms. G you're already familiar with. It's the acceleration due to gravity, which on Earth will be 9.81 meters per second squared. Let's talk for a minute about the variable h. H is the height of the object above an arbitrary reference line. In other words, we have to choose a reference line whenever we calculate gravitational potential energy. And how high the object is above that line is what this variable h is. If you look at this waiter, he's holding a tray with a chicken on it and something else. If I choose this elevation right there where my laser pointer is to be the reference line, then are we agreed that h is 0 for that tray of food? Because the tray is not any distance above that line. If, on the other hand, I choose down here by the waiter's feet to be the reference line, then h will be the distance from there to there. Or I could choose down here at the bottom of the stairs. I could choose this to be the reference line, and if I did that, then h would have the value right about there, whatever that distance is right there. So in other words, when we calculate gravitational potential energy, we really should specify a reference line. The other type of potential energy is elastic potential energy, which I'll symbolize PE elas. Elastic potential energy is the internal energy due to springy deformation. Typically when we think of elastic potential energy, we're thinking springs. The top picture here is my model of a spring that has its natural length. And what we've done here in the lower figure is we've grabbed one end of the spring and we've pulled on it, and it's stretched. And when it's stretched like that, it now stores energy. The difference in length is the important quantity in elastic potential energy. Here's the equation for calculating it. 1/2 times k. K is the spring constant. We've met it in earlier lessons when we talked about Hooke's law. The delta x is not the original length of the spring. It's not the final length of the spring. It's the amount by which the spring has stretched or been compressed. So k is the spring constant. The unit for spring constant is newtons per meter. Delta x is the change in length in meters. You want to be careful because often a change in length of a spring is reported in centimeters, but in the equation we want delta x in meters. Here we considered three varieties of mechanical energy: kinetic energy, gravitational potential energy, and elastic potential energy. For gravitational potential energy, h is the object's elevation above a reference line chosen by you. We'll show how to select a convenient reference line in the next lesson. For elastic potential energy, remember that delta x is the change in length of the spring, that is, the amount it is stretched or squished.